Is the lighting in here fine? Can everyone see everything? Hopefully it doesn't make you fall asleep. We try not to, but it is 5 o'clock nowadays. I can sometimes be soft-spoken, so if you can't hear me, just let me know. Sorry. It's my nature. But it's now 5 after, so I'll just start going through. So obviously everyone's here because you have a statistics class and you want to know more about it. So we kind of survey all the stats classes. So this will be very generalized. Hopefully there will be more specific parts of your all's course that it apply to, but I can't really get into nitty-gritty of everyone. So this will be a general overview, and it's not meant to supplement going to class. I would still very much recommend you attending the course. But going through, so what is exactly statistics? You always hear about this. At least once, sometimes in maybe high school, you start talking a little bit more about it. And then you get to college, and well, what's the stats? But it's the study, collection, analysis, interpretation, presentation, and organization of data. Data that you obtain somehow, some way. You're interested in looking into something to see if it's affected by something else. It's conventional to begin stats problems with some sort of population or a statistical model that you're interested in, and we'll get more in depth on what all these fancy words mean. But in short, statistics is what we use to deduce significant patterns versus random occurrences, and to investigate any variability within whatever one is measured. We'll go through a few examples of exactly measuring what. Just to kind of survey, what kind of stats people do we have in what classes? Sorry?
Elementary statistics.
Elementary, what about, and you said business, what about you two?
Sorry.
Sorry, okay. So, a little bit of everything. I am engineering stats. So, I think I've had about 3 different types of courses, and then I've done this boot camp twice before. So, hopefully everything is helpful, but going on through, if you have any questions, if you're confused about anything that you see, just blurt it out. You don't need to raise your hand. I'm not a professor. So a little bit more terminology here. An experiment is a test or a series of tests in which purposeful changes are made. So you're interested about something, and it has many factors that can contribute to an end result. And you change those factors. You're making those factors have purposeful changes to an input of a system, and you can observe the result. Is anything changing based on your changes? Those purposeful changes, I just said, are factors, independent or controlled variables. And your response is whatever your result is. And typically your job is to determine which factors are significantly affecting the response. And in that same term, how significant do they affect the response? So population versus sample. So you have many different sizes in statistics thing. So population represents all possible outcomes or measurements of interest in a study. So the example we have here is all the birds in North America. A sample is just a portion of that. So we look at the second one, 9,274 birds randomly selected in North America. What you're going to do is you're going to do statistics on a sample size to infer generalizations on a population. Because obviously looking at 9,000 birds is probably more logistically easy than looking at every single bird in America. That would take a lot of time. A lot of time that we don't have. The specific size that you pick, it's really weird. how you pick the size. There's certain things in statistics where you use information on previous stats on related things to choose what size to look at the next. It's called a power analysis. That's not here. The terminology. What are you going to see here? So we have a bunch of Greek letters. Likewise, math is always Greek. Mu, going to look like a U with a little stem on the left side. Mu is the average or mean of a population. Lowercase sigma is a standard deviation or variance around the mean. Right, so you might have heard in college, take a test. The professor tells you a mean or an average, and then they tell you standard deviations. It just tells you how closely packed the spread is, really. This capital sigma here is just the sum or addition of values. We'll go through exactly how to treat that here soon. You lowercase n or uppercase n, you can see either way, is the sample size. How many how many observations you have, really. Big X is the average or mean of a sample. Notice mu was specifically set aside for population. So which one's bigger, population or sample? Population. Okay. So these are very standard. These can probably change. Most likely they will change. It's going to be professor dependent, problem dependent, preference, whatever you call it. You're always going to know what variable is the mean of your sample because you're going to be told it or you get to make it. Big S is the standard deviation of a sample. So delving a little bit more into this bullet here, what this summation means. Am I good to go? Yes. So let's say, just for fun here, we have this table. Denoted little I, x of I, and y sub I. X of I, let's just say, kind of think of it right now as just a function. You put in 4, you get out 6. You put in 6, you get out 2, and so on, so on, so on. So when I say x of I mean x sub 0 is 4, x sub 1 is 6, and so on. So y sub 0 is 6, and y sub 1 is 2, and so on and so forth. Okay. So if I wanted to know each one of these guys, right here, the sum of x sub i's, sum of y sub i's, the sum of the product x I, y I, and then the sum of the subtracted y sub i's from the x sub i's. How do we go by and handle this notation here? Does anybody know off the top of your head? If you do, don't say. So let's look at the first one here. So look at each individual x sub I here. So we have 4, 6, 2, and 7. So this guy alone, the summation, or sigma notation, just means it's telling you to sum everything. Sum each one of these guys out. So we take 4, 6, 2, and 7, and we add them together. Okay? Whatever's inside the parentheses is what you're going to, it's each term of the summation. So the next one tells you to sum all of the y sub i's. So 6 plus 2 plus 9 plus 1. 18. Oh. Next, it's telling you a little bit different. What do you think we're going to do? Right, you're going to take each x sub I and y sub I and multiply them together. That's the term that you're going to add to the next multiplication. So x sub I, or x sub 1, y sub 1 is 4 and 6. So they get multiplied together. That's the new term. Add it to, x0, y0. Add that to x1, y1, multiplied. Add that to x2, y2, and so forth. You get 61. Likewise, here, you'll take each, you just do whatever's inside the parentheses for each data point you have. Okay? And then add them all together. And this type of math is pretty much going to be common throughout all stats courses because the stuff that we talk about next year is going to be a little bit more in depth. Is everyone okay with this? Okay. So don't be afraid by saying this little Greek letter C. It's just condensed math. So I've told you a few things here about population and standard deviation. and mean. So graphically, what do they really mean? So you can see here, the highest point on this bell curve, right, is mu. And mu is what? Is the mean. So the mean is going to divide everything into, if it's normally distributed, we'll get to that. Pretty much in half. No, it's not. Never mind. Just ignore that. Okay, I see what this says. So we have a population described above and a sample described below. So let's say we were looking at beak length on those birds. So all the birds here, we collected 9,274 measurements of beak length. Okay, and we made this guy somehow. We measured them, put them into categories, and we looked at their frequencies of length, and we get something that looks like this. So whenever you do stats on samples, you get what's called histograms. That's what this guy's called. Noted by the histogram. X bars in the middle here. We use this here to infer things on the overall view of every single bird. So you can sign in right there. And then standard deviation is everything on the outside. Just so you can see that way out over here, from a population standpoint at least, we have, let's call this side really, really small beak length, really, really big beak length. We have a very small area underneath this curve here, so we don't really have a lot of birds with really, really long beak lengths, whatever really long is. I'm just making this up right. How far this beak length lies from the mean is what our standard deviation is going to be. It's going to make a little bit more sense as we go through actually making things. But this is just another way, graphically looking at the relationship between a population and a sample. You're going to get very discrete information from a sample, but you're going to get generalized information for a population. The difference between a solid, curve, and just bars. Descriptive statistics. So we've already talked a little bit about this. So a statistic is a function of the observations in a random sample. So suppose we have n observations denoted as such. So earlier I mentioned beak length in birds. So let's say we had 9,274 observations. So the n is the number of observations. We can figure out our sample mean, our sample variance, and our sample standard deviation by looking at the mean is the sum of all of your observations divided by the number of observations. You've done that probably since middle school at the minimum. Sample variance, and we start saying all of this sigma notation, but notice, don't be afraid of the numbers here, the 1 to n. It's just telling you to sweep the entire set of observations. Starting, this could sometimes be 0, sometimes be 1. It's personal preference, right? I started at 0. That's just what I've been accustomed to learning with. So here, you're just taking the observations, summing them all together, dividing them by n. Here, you're going to be taking each observation, subtracting the previously calculated mean. That result squared. Summing that to the next observation, subtract the mean, square it, and so on and so forth. And then you're going to be dividing by n minus 1. That's just standard. You're going to get what's called s squared, which is the sample variance. The square root of that is your standard deviation. Okay, so I have a quick Excel document here. So how familiar are you all with Excel and working with it to do stuff like this, math-wise? Kind of iffy. So I just have a couple of different numbers here. So things I was looking at before, last week. I was looking at cell death based on different conditions of cell environments. And I got these numbers. I'm not going to tell you what they are because they're not important. If I wanted the sum of each one of these guys, and they're in the thousands, so it's going to be kind of easy. In Excel, wherever you want to put your numbers at, you just, on your keyboard, you're going to be hitting the equal sign. And there's a couple of equation shortcuts within Excel. The sum is really easy. You just type sum. Open parentheses, and that's, Excel tells you number 1, comma number 2, so forth, so forth, so forth. But you can just select every number that you want it to sum by clicking and dragging and holding all the way down once you have all your numbers selected. Close your parentheses, and Excel will pop out the sum automatically. If you have it set up like mine, you can just click and drag that same equation through multiple columns to get the same equation, but just minimizing the amount of work you have to do, the amount of keyboard stuff. Because notice what I did. I went up here and clicked in this formula bar, and Excel is telling me exactly what's going on. I'm taking the sum of C2 to C8, and it's highlighted C2 to C8 in blue. So it's a way of double checking to make sure you're doing things right. Likewise here, it should highlight the next ones, and it did. So now I need to find the mean, so I'm going to tell Excel to take this guy and divide it by 7, because there's 7 of these. 1, 2, 3, 4, 5, 6, 7. Every time you do any type of math in Excel, you have to have the equal sign. Excel doesn't know to do anything else, to do math, unless you have the equal sign. And then the division is just this little backslash. Likewise, just click and drag it through the column. You'll get this. So this will be the mean of each one of these guys. So about 3,600, and you can kind of look at the spread here and be like, okay, I can believe that. We have 2,800, 40, almost 4,700 here. So 36 would be about right, roundabout. So now I'm going to work with trying to figure out this guy, sample variance. Show you how to do that. So it says to take each data point and subtract the mean from it. So that's what I'm going to do here. I'm going to tell Excel to take the first data point. Sorry, what did I not do yet? Did not hit the equals. Hit the equals. Now, take the first data point within my first condition, what I'm calling NP. Subtract my mean. And then I'm going to put this into parentheses. And in Excel, to get the square here, what you're going to do is, you've always seen this little keyboard here, with this little funny symbol, the little caret right there. It's Shift 6. That just means raise 2 in Excel, and you just hit 2, and that you're telling Excel to square that number. Okay, there's one small caveat here. So look at what happens when I click and drag all the way through. I start getting really big numbers. 4.9 times 10 to the 158th is nowhere near a number I should get. And here I don't even have a number. So there's a small problem here. What I told Excel to do is I made this first cell here correct. Observation here minus the mean, that results squared. But what Excel, whenever I click and drag and carry the formula all the way through right here, because you'll just click the little square and go all the way down. What Excel is doing is it's moving. Notice both of these numbers increased. So B3, it went ahead and moved on down to B3 for me and subtracted. It did not subtract by mean, but it subtracted the most previous result. So it's going to go down all the way. So I want to tell Excel to just use the mean. I don't want it to move. Okay. So what I had to do is put dollar signs around the B. And that tells Excel to hold, to not move from B12 to continuously use B12. So next time I move through this, all my numbers changed. And they're all relatively in the same ballpark. I can carry that all the way through here, except here I will have to change this guy to C12, because its mean is in C12, right here. And then this guy will have to be D12. Now I can move on. So I have, at this point, each x minus the mean squared. I do not have their sum, which I did not put in a spot here for. So I'm going to come here and say, okay, I have the math part done. X minus the mean squared. Now I'm going to sum that together. And divide by n minus 1, which is 6. So our variance should be the variance is not really used as much. The more important number is going to be standard deviation. So what I have to do is take the square root of what I just found to get my standard deviation. And in Excel, you just type in square root, SQRT, for square root. Tell it the number, and hopefully this number is the same as the other. Okay. So, luckily, I just did this for demonstration purposes. Excel has a formula called STDEV, standard dev, that you can also use. You don't have to go through this hand calculation every single time. I just did it to make sure I was doing things correct. But it just looks at this data and takes the standard dev. It has all that math packed within that formula. Yes?
So we don't have to program that formula in the Excel, right? So
No, it's already there. It's standard. I just went through all this to show you exactly what was going on and how you handle working with this equation. Some professors might actually make you do small things along, just to make sure you get things figured out. I know the math is probably the most sucky part about this class, or any of the stats classes. So we just calculated standard dev with something. So what does standard dev tell us? It's the variation around the mean. It's how much variability lies within our actual set. You want really low standard deviations, because that just tells you that you have really good data. If you have high standard deviations, there might be something going on, there might be an outlier, or whatnot. So I always use the example that one of my physiology classes, we had a test. The average on it was like a 62, and the standard dev was a 23. And I don't know, in college world, standard dev of 23 is really high because it tells you that the first standard dev, a majority of the class, was centered around a 62, but varied anywhere between 22. So 42, anywhere between 59 and 85, the majority of the class was there. Because the first standard dev right here holds, I don't know why that says 68.3. Yeah, it should be 68.2. One standard dev away from the mean is what this means. Mu minus sigma, mu plus sigma. 68.2% of your observations will lie one standard dev away from your mean. That's just kind of a general, as long as everything is right with the world, that's generally the way it's going to work out. So what that example tells us is that about 68% of our class is anywhere between an F and a B. And that's pretty big. if you were looking at things, that would come across as kind of shocking. If you have a really high standard deviation, it's a really large spread, large data. Low standard deviation is a small data. Values are really close. We have this thing called normal distribution that you should keep in mind. What it pretty much means is that everything is symmetric. So the mean is close to the median, is close to the mode. Do we remember what median and mode mean? What's median?
The middle number in the data set.
Right, it's the number that splits the data set into half. Okay. The mode,
Most occurring.
right, the number with the highest frequency. So approximately 50% of the values are less than the mean, 50% of the values are greater than the mean in a normal distribution. This is where you hear the term bell curve. Professors try to normally distribute grades across the class. I don't know what any of these axes are. But most of the time, data, just because I don't really have a great reason why, other than there's a slide in here that tells you it. Most data that you work with is typically normally distributed for what you work with. Just a couple of odd and end definitions that could come up. Negative or left skew, positive or right skew. It just means that the relationship between the mean and the median is not, they're not exactly the same. So here you can see in a symmetric, so if the median is really close to the mean, you have this really nice distribution here, nice and even. If your mean is less than your median, you start to have this left skew here. So things are kind of shifted to the right. Because the median just kind of splits things in the middle, but where things tend to lie on average is where the mean is. So it's the opposite for a positive skew is if the mean is higher than the median. You start getting this little effect where things are skewed to the right. You don't really see this a lot, but I have to talk about it. More important things. Histograms, I've already touched on a little bit, and we'll work with one here soon. So what they did is they measured heights of black cherry trees. Heights ranging from 60 feet to 90 feet. And then we have this word frequency pop up, and these are just number of observations. So what they did, whoever did it, wanted to know, I have a bunch of black cherry trees in the back. I want to know what's the spread of cherry trees and height back there. So anywhere between 60 to 65 feet, there were 3 trees that they measured. This bar is between 2 and 4, which is 3. Same way, anywhere between 65 and 70 feet, you had 3 more trees. Okay. So far you can get the total number of observations from a histogram because this person did 3 plus 3 plus 8, so that's 14, plus 10 is 24, plus 5 is 29, plus 2 is 30, he measured 31 trees. Okay. Out of that, 3 of them were between 60 and 65 inches. 3 of them were between 65 and 70. Most of them lied between 75 and 80. Not inches. So this is kind of how you read a histogram. The leaf, stem, and leaf plot is really just a numerical way of looking at the same thing. Notice if you have numbers like this here, your stem is the tens place and your leaf is the ones place. You can see, I don't know, let's say this was also heights of black cherry trees. You can see 2 of them were between 40 and 50 feet. 1 of them was between 50 and 60. 1 of them was between 60 and 70, or 60 and 90. I don't know why the jump's so high. But it's pretty much the same way just to get that. Because if you were to tilt this around and rotate it, it would have a similar shape. So I'm sure if we knew the numbers behind this, we could make a stem and leaf plot that tell us the same exact thing. Number of observations from the stem and leaf plot, we just count how many of these guys there are. 1, 2, 3, 4, 5. This guy only measured 5 trees. I believe the person on the left has measured 31 trees. Scatter plot starts to explain, this is actually in a core spot in the PowerPoint. If you want, in this case, let's say you were looking at to see if there was a difference in income per year of a professor versus years of experience at the university. You wanted to see, is there any type of correlation? So you measured a bunch of data. You measured 1, 2, 3, 4, 5, 6, 7, 8. You measured 10 people, 10 dots, 10 people. You found their years of experience. You found their income per year. You plot income per year versus years of experience. You can do this in Excel pretty easily. It's not terrible. There's a graph button. There's tutorials to let you do it. But what you see is that this tends to go upwards, right? So it would make intuitive sense, the more years of experience, the more income you make. And you wanted to justify to see, is that true? So you see here, because this has a general upwards trend, you call that a positive correlation, meaning that more years of experience gives you more money. Unless you have 35 years of experience, you actually make less. I always thought that was interesting. 25 makes less than 20. 30 makes more. It's interesting. We'll talk more about this too. There's different types of correlations you can have. But I wanted to go over this concept of frequency real quick, because I noticed a lot of things popping up last semester that I didn't talk about. So let's say you're in a class and you have the following grades on all your assignments. I think there's 30 here or something like that. So you can just look at the numbers. The numbers there aren't really important. But you're interested to seeing your spread or frequency of grades to evaluate how you're doing in class. So you separate your grades into groups. You choose how you want to separate things based on what you're most curious about. This person here decided I want to see, where do I where does the majority of my grades lie between letter grades? You will sometimes hear this as bins in Excel talk. We call them groups. Excel calls them bins. Okay. So you can scan these here and see that any number between 41 to 50 is right here. So there's a 42 here. And there's a 42 here. And it's all grouped based on this classification. And I want to know relative frequency once I get to this point. Okay, so I've grouped them all together. You can kind of hopefully believe that these are all the numbers. And we want to look at relative frequency. The equation for such is up here. It's your relative frequency is the number of observations within your group divided by total number of observations. Okay. So between 41 to 50, we have two numbers. We have a total of 30 grades. So relative frequency is 2 out of 30. As a decimal, that is 0.07. As a percent, you just move the decimal to the right 2 places, and it becomes a whole number. So 7%. Then you have this other term called cumulative frequency. Notice the first one here is the same as the relative frequency. But let's look at 51 to 60. We had 5 grades between a 51 to a 60. That is 17% of our grades 17% of our grades are basically in F. But cumulative frequency changed. What did you notice? How did it change?
It goes up by 7.
Right, it goes up by 7. 7 just happens to be the most previous number over here. 17 and 7. So you just add these two. So what that tells you is that actually 24% of your grades are an F or below. Okay, 60 or below. I believe 60 today. Yeah. So you start increasing your cumulative frequency to start seeing information just as you go along. 37% of your grades are at a 70 or below. 47% are at an 80 below. But does everybody understand the general concept of relative and cumulative frequency? I had a lot of questions on those last semester. So here, you just kind of draw random conclusions from frequency plots like this. So 30% of your grades lie at a 91 or above, which is pretty good. But also keep in mind that 24% of your grades are at an F or below. So you know there might be something there. You start trying to get more A's versus less A's. It's really just an organizational way of looking at data. Just trying to see where do things align, right? Then you can do your average grade and then your standard deviation for others too, if you want it. For the sake of time, I'm not going to go over box ones. This is that one random thing called the central limit theorem. Given certain conditions, the sum of a large number of independent random variable values will be approximately normally distributed. That's just a fancy way of saying if you have data you're working with, you can just assume that it's normally distributed if there's enough data there. There's ways that you can find out to see if that's not the assumption, but I feel like that's more advanced stats that you don't need to know at this point. Normally distributed is what you typically think of as a bell curve. So correlation, going back to this a little bit, how strong is the relation? Yes.
Did you go back for like 2 seconds?
Yes. I'm going to send the PowerPoint to each person too.
Oh, okay.
If that helps at all. So how strong is the relationship among means, or is this relationship positively or negatively correlated, or none whatsoever? So 3 examples here. You want to know, does the, let's say, you want to know, does the number of foreclosures have any effect on the number of household units available? And then you get a lot of information on foreclosures based on your number of houses on the market go up or down, or stay the same. So you can notice as foreclosures go up, as more people forget to pay their house or just stop paying on their house, then more household units become available, right? So as foreclosures increase, the number of houses for sale increase. Okay, household units. I don't know why it's called that, but it is. So there's a strong positive relationship because it's going upwards. On the other end, if you have something like this that's going downward, it tells you as unemployment rate increases, you start to notice a correlation between the amount of unemployed people that don't have a college education. Less unemployed people are more college educated. More educated college. I don't know how to say that. I've been here 6 years. I don't know how to say it. But there's a strong negative relationship here, a negative correlation. Let's put that up. Again, someone was interested in seeing, is there a relationship or a correlation between the percentage of people who have college education versus do they own pets? As you can see, there is no correlation. Lower college educated people could have, maybe this is 2 pets, could have 10 pets. 5 years of education, this guy only has 1 pet. There's no correlation. How do you measure a correlation? You get a coefficient of determination and a correlation coefficient. This R squared is your more important number. Range is 0 to 1. R squared closer to 1 indicates that the data fits the line well, or that there's a strong correlation there, whether it be positive or negative. You have to graph things to figure that out. Closer to 1, stronger correlation. Less than 1, closer to 0, there's a weaker correlation there. I'm not going to mention much about color because it's not really important to be honest. Okay, so a lot of this beginning stuff is a lot of what I just called beginning stuff. Statistics, descriptive, describing things, correlations. You're going to use a lot of your descriptive statistics and your knowledge of correlations to start figuring out what's called confidence intervals. Somebody comes to you and knows that you've done a study on those 9,274 birds. You measured their beak length. You looked at different correlations of different birds in different areas. You have the mean. You have standard deviation, and they want to know if I pick this amount of birds in this area, what is an interval of beak length that I can reasonably assume that I will find? And that's the confidence interval, an interval of whatever you're measuring with up to a certain level of confidence, and there's a few different ways. The range of values with a specified probability that the value of that parameter or thing that you're measuring lies within said interval. You'll have a lower limit, you'll have an upper limit, and you've already found the mean. You'll hear phrases like compute a 95 and 99% confidence interval. Typically, you're going to be working with 95% if your class does in fact go through this. But there's typically 3 different types. There's 90, 95, 99. You really don't want to go anything below 90 because that tells you that there's 10% chance that you have no idea what's going to happen. People are generally more happy with saying that there's a 5% chance that something different could happen. Because 5 is a relatively low number. 1 is better, but as you get closer to 100, it's like a weird paradox. Somebody really likes 95. And I know I've heard the reason why before. I can't really remember it. So most of the time you'll be creating a confidence interval about a mean, because that's typically the most interesting thing that someone's going to look at. So what this says here is there's going to be some, let's say this was beak length, awesome, that if you took birds from a specific area, you would find birds that have an average beak length in that area from 25.77 centimeters to 26.87 centimeters. Okay. How do we get this? I'll show you on the next slide or one after. But there's this, whenever you say a 95 or a 99% confidence interval, you're talking about this little part right here, 100 times what's 1 minus alpha. You're always going to hear an alpha of 0.05 or 0.01 or 0.1. It's all going to be based on what type of confidence interval you make. The confidence level is 1 minus alpha percent. So a 95% confidence level is 100 times 1 minus 0.05. Because 1 minus 0.05 is 0.95. Times 100 is 95%. So it kind of shows you the relationship here. 99% alpha 0.01, 95% alpha 0.05, 90% alpha is 0.1. Here's the reason why you don't want to use 100% confidence. It's all based on the precision of your estimation. The wider the confidence interval, the more confident that you are that the interval actually contains a true value. The wider the confidence interval, the less information we have about the true value. So an ideal situation is a relatively narrow interval with high confidence. So that's why we typically rely on the 95%. It's relatively close to 100. 95% is a pretty good number. Everyone would be happy with a 95 on something. But the caveat here is that you generally have to have large sample sizes to be the most accurate for people to really believe you. Don't be afraid by this equation here. So this is how most people will be calculating confidence intervals. You will be given a mean, because or you found the mean, this guy, x bar, x bar. You will learn, if you do use this equation, you will learn what this means. This is just a value in the table. You will look it up, you will have a table, you will know what alpha is, you will divide it by 2. You go to a table, you will find z, whatever. S is just standard deviation, n is just sample size. So all relatively easy things, you just have to be familiar with the table. I'm not going to go through the table because not everyone might use it. Like I said, this is a very general. But what it means is that this confidence interval will be centered around the mean. It has an upper and lower limit. Lower limit here, upper limit here. Notice that as the sample size increases, your confidence interval width decreases. You get more precise as you get more observations. The variance of theta, however, as variance increases, your confidence interval increases. And that kind of makes sense. If you have more variance, if things lie farther away from your mean, your confidence interval is going to have to account for that change, right? It's going to be bigger. And here's just a little graphical line describing what this math right here means. Again, don't be afraid of this. I know it's a lot, but it's really easy. So confidence intervals start leading us into a null and alternative hypothesis testing. Some of you guys will be doing hypothesis testing. You're going to want to know, for example, down here, the average height of girls in 2 different groups, Group A and Group B. You want to know, do they have the same height, the same average heights? Do they have a different average height? You don't know. So H sub 0 is the standard notation for a null hypothesis. So down here, H naught is, you're saying that both groups have the same average height of 5'5". The null hypothesis is that both groups have the same average height. That's your initial guess. You need to do confidence interval testing to disprove or improve yourself. The alternative hypothesis is always the negative of the null, which is the opposite. So this is where we're going to start trying to find, are things patterns or are they variabilities? And if they are patterns, or if it is a variability, how significant is that pattern? Basically, how reliable is that pattern to pick up on? You're going to start using what's called a p-value to answer questions. I took this slide. I like this slide much better. When we reject the null hypothesis, when your p-value is less than alpha. So you're going to learn how to calculate the p-value if you're going to use it. So typically, you have a the wording would be like compute if there's any statistic difference between the 2 girls with a confidence interval of 95%. That tells you right there that alpha is 0.05. So in the process, you will learn how to calculate p-value. So if you find something that you think is different, the p-value, if it's less than 0.05, tells you that it would be statistically different, meaning that it's significant. It actually matters. If it is any number above 0.05, if it's 0.051, it's useless. Smallest level of significance that would lead to rejection of the null hypothesis. How strongly we believe H naught or H1. If you get a p-value of 0.0000, you can pretty much strongly believe your null hypothesis. You're not going to reject it. And this is how important decisions are made for like manufacturing processes or really odd new things. all of the modern medicine that you use nowadays, Tylenol, ibuprofen, NyQuil, they were all tested beforehand to see their significance. Did they really statistically lower whatever they're trying to act on? A lot of people did a lot of stuff. They did all this type of hypothesis testing and they figured it out. So a very brief overview of just about everything at an undergrad level. Is there any questions? Like I said, I'll send a copy of this PowerPoint to everyone. And there's a survey there, if you can fill that out for me, that would be great. If there's no questions, then everyone's free to go after you fill out the survey. You can just leave the surveys where they're at. You don't have to take them anywhere. Once you fill them out, you can just go on home. Good luck, everyone. Have a happy semester. Spring is always very short. It's also very quick. Keep in mind.